All right, so let me turn on the recording monitor. There we go. Testing, testing. Okay. So more SICP. Oh, I've last time on the last video I was stuck on exercise 110. And I figured that out on the fallible ideas list. So I recommend if you're interested in seeing where that went, you can check that out. The name of the number of the problem is in the title. It's like SICP exercise 110. I might make a PDF of it. I was gonna put a PDF. I was gonna make a PDF in MailMate, and put it of the thread and put it on my blog, but for some reason MailMate, the output to PDF was coming out in black and white, and I didn't want that. I wanted the quote coloring, so I'll have to figure that out. But anyway, so I'm picking up where I left off. I've finished this problem, and so we're going to do tree recursion now. And I have some text-to-speech software installed in Google Chrome, but I'm looking at this content, I don't think it'll be super great for it. So I'm just gonna, if I get to like a larger block of just text with no code, I might try it out. But since it's like code and images and stuff, I'll just read it out for now. Okay. So another common pattern of computation is called tree recursion. As an example, consider computing the sequence of Fibonacci numbers, in which each number is the sum of the preceding two. The Fibonacci sequence is something they like to use in math and talk about in math stuff a lot and learning materials, because I mean it's interesting, you know, like the way it sort of unfolds. In general, the Fibonacci numbers can, because you can reduce it to, you know, to a pattern. In general, the Fibonacci numbers can be defined by the rule fib n if n is 0, 0, if 1, 1. Otherwise, fib n minus 1 plus fib n minus 2. All right, and we see they define a recursive procedure for computing Fibonacci numbers, and then they give us an actual diagram, which is pretty helpful. Let's, you can see that they've represented this rule in code, and I think it's pretty straightforward. Like these parts are very straightforward, right? It's just, you know, of 0, 0, of 1, 1, and then this is a little more complicated, but it's just, you know, another a couple of recursive calls to fib, like we've been talking about. We've got, and the sum of them, we've got n minus 1 and n minus 2. And they go through 5 to show what actually happens. And so you can see out of fib 5, we get fib 4 because of n minus 1, and fib 3 because of n minus 2. And I think the n minus 2, the fib 3 is it's smaller, so I'm going to consider it first. And it's a good illustration of like how the procedure works, because it's like small, but it's also it winds up using both of these cases, so it still gives you a pretty good sense. So fib3, which, we got to from fib5 and then n minus 2, this winds up being its own recursive calls. So now we would have like fib3, and then is, n is 3, so is n 0? No. Is n 1? No. So then again, we would take the 3 and we do n minus 1, so then we get fib2. I just realized I should turn on Demo Pro since I'm like pointing at things. So, oops. All right, so out of this fib3, we get fib2. This is the n minus 1. And then the n minus 2 gives us fib1. So now we've gone down a couple levels. So you see, even just going from fib3, we still have to go down a couple of recursive levels. So this fib3 gives us the fib3 into this n minus 2 call gives us fib1, and that finally lets us return a value because n is equal to 1 then, and so then we get 1. But then the other call that comes out of the fib3, fib2, doesn't meet either of these conditions. So then we see it's again 2 minus 1, so then we get fib1, and then 2 minus 2, so then we get fib0. And then those both produce values because n is 0 in one case and 1 in the other case. So then we finally get to the basic case in all these. I thought it'd be a good idea to show what like the fib program is actually doing. So like, because you could sort of get the idea, but like they don't actually say. So you give it 0, 0, and so on. Notice we got 0, we got 1, then we got 1. All right, this will be an even better way to show what's going on. So we do fib0. I turn trace on. By the way, I discovered if you're using the SICP Dr. Racket package or language or whatever it is, that doesn't support trace built in like by default, but you can use this, the hash or number sign or whatever you want to call it, and then %, and then require bracket / trace. And if you put that at the beginning here, you can use trace, and then you can make it a lot easier on yourself to understand what programs are doing. I think a lot of the use of Dr. Racket is for learning, so it's an especially useful thing. And there was another way of making this declaration. It might have been with the without the number sign or whatever that I saw, but that didn't work. So you need both these elements before the require, and then it'll work. And you're basically importing the trace program from like a Racket library into SICP, something like that. which is cool. So we see here nothing much happens because it's basically, it just evaluates fib 0 and that's it. And it sees, oh, there's, n is 0, so then I'm done. And similar happens fib 1. Then we get into fib 2, and then we see that some stuff actually starts happening. And this is actually really cool. So we already essentially have a diagram for fib 2, which actually, really, it's this whole chunk here, right? This is basically this. This is just presented, in text and like, on a prompt, and this is visually and vertically. But it's like it's very similar information. We see that we give the fib procedure 2, and then it breaks it down into fib 1, which we have over here, and fib 0. And fib 1 returns 1, as we can see. The same over here, and fib 0 returns 0. Tracing stuff is cool because, like, we're not going to have diagrams for everything that we want to figure out. But if we understand what's going on, what's being represented in this, then, we can see into any program that we want to. We don't need the diagram to exist already for us. I guess you could do something like that S tree thing, that S expression thing that Elliot made, and just like diagram any arbitrary program flow. Well, not any arbitrary program, I guess, but like at least a simple program like this. It's just has just like the straightforward nodes or whatever. Because I guess some it wouldn't be practical, but anyway, there's a tangent. Let me make this. Okay. So Fibonacci 2 is like when we start getting interesting things happening. And so we return a 0 and a 1, and the procedure it sums up the results of these recursive calls. So that's one way to think about, like, why are we getting, when we do Fibonacci 2, why do we get 1? Because that's the sum of these recursive calls. And so then I'm going to do it up through 5. So we do 3 and Fibonacci 3, and we already basically have that diagrammed. And you can see, there's a recursive call to 2, fib 2, or there's a recursive call to fib with 2, I guess I should say. Yeah, I think that's, anyway. So we already went over that. So that's going to be 1. And then there's also, or another recursive call to fib with 1. That produces 1. So just looking at this, even if you didn't know, if I did that right, yeah. Even if you didn't know about Fibonacci numbers much, if you know you just got to add these up, then fib 3 is going to be 2, right? And that's That's what it is. So it's the Fibonacci sequence or procedure. The way what we're getting out of it is like we give it a number and it tells us in the sequence of Fibonacci numbers like what, which is a special sequence which follows these rules about the number being the sum of the preceding two. What Fibonacci number is that n that we're passing in? You can think of we have the like dot 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 here, but this is extending off into infinity, basically. You know, like following the rule. So you can see if you're just adding up the previous two, and the next one's like 34, and it just keep going on. And so what this program is doing conceptually is like it's basically calculating what the Fibonacci number is going to be. Is that by like applying its rule until essentially it has a bunch of ones, because there's zeros that are returned, but like those, I mean, they matter, but it's like in a sense it's really the ones that are going to be added up, because if you add a zero, you don't change the number. So it uses recursive calls and then adds up a bunch of ones to figure out what our Fibonacci number is. And you can see the complexity of this scales up pretty fast. Like, 1 is nothing, 2 has a little bit going on, 3 has more, and then 4 you can see it visually too, right? Like, this Fib4 stuff is much bigger than the Fib3. And then the 5 is even bigger than that. So it's not long before the computer's doing a lot of work that would be tedious for a human. We'll do Fib5. Yeah. Now that's like scrolling, right? And again, this is just a line of text representation of that, basically. So the tree recursive process generated in computing Fib5. Consider the pattern of this computation. To compute Fib5, we compute Fib4 and Fib3. To compute Fib4, we compute Fib3 and Fib2. In general, the evolved process looks like a tree, as shown in 1.5, in figure 1.5. Notice that the branches split into 2 at each level, except at the bottom. This relates to the fact that the fib procedure calls itself twice each time it is invoked. The procedure is instructive as a prototypical tree recursion, but is a terrible way to compute Fibonacci numbers because it does so much redundant computation. Notice in figure 1.5 that the entire computation of Fib3, almost half the work, is duplicated. What they're talking about is you have this, and then we have this. And that's not ideal. Also, we have the 2's are duplicated, and yeah, there's a fair amount of duplication. In fact, it's not hard to show that the number of times the procedure will compute fib1 or fib0, the number of leaves on the tree in the above tree in general, is precisely fib n plus 1. To get an idea of how bad this is, one can show that the value of fib n grows exponentially with n. More precisely, see exercise 1.13, fib n is the closest integer. All right, I'm trying to lose me a little bit. I don't even know what that thingy is. Can I paste it? That looks like an image. Yeah, save as image. Oh, I'll delete that. What is the closest integer to something? All right, I looked up the symbol, and it's a Greek symbol phi, I think, which they're just using to represent the golden ratio. Like that's what it means. Okay. So the upshot, thus the process uses a number of steps that grows exponentially with the input, meaning the process for the generating or calculating Fibonacci numbers that we were just going through and talking about. On the other hand, the space required grows only linearly with the input, because we need to keep track only of which nodes are above us in the tree at any point in the computation. So they say, in general, the number of steps required by a tree recursive process will be proportional to the number of nodes in the tree, while the space required will be proportional to the maximum depth of the tree. I guess that makes sense, because number of steps. Yeah. And the linear. One way of thinking about it is like when we increase fib or the n of fib1, we're adding, like going from 3 to 4, like we're adding this whole chunk, which is a lot, over what we were doing before that. I didn't draw that perfectly, but we're actually only adding like one level of height. And going from 3 to 4, there's just like that one more step. So there's a lot of, we're adding a lot of steps with each increase, but not necessarily a lot of depth. I think that's related to what it's talking about. All right. We can also formulate an iterative process for computing the Fibonacci numbers. The idea is to use pairs of integers a and b, initialized to fib1 and fib0, and to repeatedly apply the simultaneous transformations I'm not sure what the arrow represents exactly. I'm just going to read on. It is not hard to show that after applying after applying this transformation n times, a and b will be equal, respectively, to fib n plus 1 and fib n. Thus, we can compute Fibonacci numbers iteratively using the procedure to find fib n, fib iter 10n, and find fib fib iter a b count equals 0b. All right, so using trace, we can get a pretty good sense of how this program is working, and along with their description of it. So they say the idea is to use a pair of integers a and b initialized to fib 1 equals 1 and fib 0 equals 0, and to repeatedly apply the simultaneous transformations a plus b to a and a to b. And the way those transformations are reflected in the code is, so you'll notice in the fib iter part of the program, which is the part that's doing most of the work, we have a, b, and count. So that's 3 parts. But then when it makes a recursive call to fib iter again, it's passing in the sum of a and b as the first thing instead of, it's not passing in a again, but it will be a in the recursive call. And then, so that's the AB to A, and then the A is going to be B in the recursive call. So that's this part. So, and that's how it does those transformations. And then it decrements the count by 1, and that's basically how it works. So if you give it fib iter, or fib 5, I should say. I'll wipe this out. So we start out, and so I did trace on both parts of the program, on the fib and the fib iter, but you can see the fib iter is what's doing most of the work. So we see that our initial values in fib iter are 1 and 0. And if we do fib 5, let me just do it again down here. There we go. If we do fib 5, then the count is 5. So we see that our initial values, that's where they are, right? In the program, 1 and 0. And then what happens is that, so 1 is A and 0 is B. Those are added up into 1. And then, or I'm jumping ahead. I'm skipping steps. So the count for fib 5, the count is 5. So the count is not 0. So we're not returning B or anything yet. So then we get to fib iter, and so we do this recursive call. So then we take our A and our B, which start off at 1 and 0. We add those up, and those are going to be 1 and 0 is 1, right? So, and then for this recursive call, we for what's going to be the B in the call, we give it A. So that is so that's why you see the second step here. We have 1 and 1 because we've added up A and B and gotten 1, and then we're passing in A as the second value, and that's also 1, and then we're decreasing the count by 1. So all that should make sense. And then so it carries on. So once again, if we have fib iter 1, 1, and 4, well, the count is not 0, it's 4. So then we have to do the recursive call again. But now when we add up A and B, oops. And now when we add up A and B, because we have A1 and B1, we're going to get 2. And then that's going to be the first value. And then the second value is going to be 1, because that's what A is right now. And then we're going to decrement the count again to 3. And it's going to continue on. So that I think is enough steps. You could see just visually, like you see how like for fib 0 there's like one real like step with this like 3 valued thing going on. And then in fib 1 there's 2. Fib 2 there's 3. Fib 3 there's 4. So you see how it's going up by 1, the number of steps we have to do. And you see how that's very different, visually even, from the huge like explosion of steps. Like when we were doing the other approach. It's like 2 didn't have that much, 3 started getting along, and then 4, and then 5 was like a lot already. So you see this approach scales up a lot more nicely in terms of the number of computations. Right. The second method for computing fib n is a linear iteration. The difference in number of steps required by the two methods, one linear in n, one growing as fast as fib itself, is enormous even for small inputs. One should not conclude from this that tree recursive procedures are useless. When we consider processes that operate on hierarchically structured data rather than numbers, we will find that tree recursion is a natural and powerful tool. But even in numerical operations, tree recursive processes can be useful in helping us to understand and design programs. For instance, although the first fib procedure is much less efficient than the second one and is more straightforward, being little more than a translation into Lisp of the Fibonacci sequence, of the definition of the Fibonacci sequence. Yeah, I think I said that even. It's just like it's barely, it's very clearly, these two things are related to each other. Where was I? To formulate the iterative algorithm required noticing that the computation could be recast as an iteration with 3 state variables. It takes only a bit of cleverness to come up with the iterative Fibonacci algorithm. In contrast, consider the following problem. How many different ways can we make change of $1 given half dollars, quarters, dimes, nickels, and pennies? More generally, can we write a procedure to compute the number of ways to change any given amount of money? I tried seeing if I could come up with a solution on my own. The outline of one mentally, but I was a bit stuck, so I'm just going to read on since they seem to describe it. So this counting the number of ways to make change problem, they say, has a simple solution as a recursive procedure. Suppose we think of the types of coins available as arranged in some order. And then the following relation holds. The number of ways to change amount A using n kinds of coins equals the number of ways to change amount A using all but the first kind of coin plus the number of ways to change amount A minus D using all n kinds of coins, where D is the denomination of the first kind of coin. Right, so what they're at least saying here, like just to use concrete examples, I don't really get it yet, but I just want to get it out of the A and N realm. So the number of ways to change amount, say $1, using, what was it? 1, 2, 5 kinds of coins equals the number of ways to change $1 using all but, let's say, $half plus the number of ways to change A minus D, where D is the denominator, using all n kinds of coins, where D is the denomination of the first kind of coin. So this would be, because $half is 50 cents, so this would be $1 minus 50 cents, 50 cents, using all 5 kinds of coins. So just getting it all out again with the concrete values plugged in, the number of ways to change $1 using 5 kinds of coins equals the number of ways to change $1 using all but the $half plus the number of ways to change 50 cents using all the coins. And so now they're going to say, so why would that be true? To see why this is true, observe that the ways to make change can be divided into 2 groups. Those that do not use any of the first kind of coin and those that do. Well, that makes sense, sure. Therefore, the total number of ways to make change for some amount is equal to the number of ways to make change for the amount without using any of the first coin, plus the number of ways that make change assuming that we do use that first kind of coin. Well, that's true. Like, I have no objection so far. But the latter number, okay, so this is but, so this but is going to be something tricky may follow it. But the latter number, meaning the number of ways to make change assuming we do use the first kind of coin, is equal to the number of ways to make change for the amount that remains after using a coin of the first kind. Right. So I just was having some trouble with this part specifically, but the latter number is equal to the number of ways to make change for the amount that remains after using a coin of the first kind. I'm having some difficulty like parsing that, I think, and also understanding why it needs to be true. So I asked the chat room. We'll see if anybody responds with anything. They might respond, but like not right away. So I found a site that is at renomad.com, this guy's blog, where he's got this post working through the SICP, counting change, and he makes some comments, including, he says some stuff where the book sort of frames it as like, oh, this is not so hard to figure out, which is not great. Like, on the one hand, if you think about it in like in the context of the audience that they had in mind that they were addressing when they wrote the book, where it's just like MIT students or whatever, then it kind of makes more sense. But it's not an optimum, and presumably even some of them like had some trouble with this stuff, so it's still not great. But then it's really not great if you're like somebody who's not in the position of somebody with that background, and then the book is like, oh yeah, this is like, you don't have to be so clever to figure this out. But on the other hand, you've got to like have some resilience. But anyway, tangent. So this guy did this very nice little text example, which I've pasted here because I don't like scrolling. I don't like this scrolling frame thing. It really annoys me. Let me, too many monitors moving around. Okay. So basically, this is the crux of this counting change thing. The number of ways to change amount A using n kinds of coins equals the number of ways to change amount A, meaning to make change for amount A, using all but the first kind of coin, plus the number of ways to change amount A minus D using all n kinds of coins. Okay. So what that boils down to is basically if you're assuming that you use the first kind of coin, okay, here's one way to think about it. The exact number of coins that you're going to use in any given case, it's going to vary some depending on whether you're using more pennies. But you could still think of them as being like ordered in a way. So like you could think, well, there's like a first coin that you use and a second coin. And so one way to think about it, and this sort of parallels how this is organized here. If you're assuming that you do use the coin with the largest denomination of the coins that you have, then that coin is going to be in like the first slot, so to speak. And so it's going to be like a constant. And the only difference, there's always going to be that dime in that like first slot. If you were like arranging the coins, from left to right or something, they always have a dime there. And then the only thing that's going to be different is the coins is do you have 2 dimes? Do you have a dime and 2 nickels? Do you have a nickel and 15 pennies? That's going to vary, but if you, like I said, if you have the coins arranged from left to right, that leftmost coin is always going to be a dime. If you are assuming that you're making change using the first kind of coin, it's just like a definition, almost like, well, assuming we're using the first kind of coin, the highest denomination coin, then we're going to be using it at least once. And so when you have that assumption, then like I said, the part that varies is the rest of it in terms of the distribution of the coins. And that fact, the fact that the part that's like different each time, of the subset of cases where you're using the largest denomination coin, the fact that the part that's different is like the rest of the coins is the reason why this stuff is true. Because this is the part where I was getting really stuck on, where it said, okay, so the total number of ways to make change for some amount is equal to the number of ways to make change for the amount without using any of the first coin. I haven't talked about it yet. We'll talk about that in a second. Plus the number of ways to make change, assuming that we do use the first kind of coin. That's what I've been going on about so far. But the latter number, meaning the number of ways to make change, assuming that we do use the first kind of coin, is equal to the number of ways to make change for the amount that remains after using the first kind of coin. And I was like, well, why? Why is that the case? Well, it's the case because of what I was just saying. That assumption, assuming the number of ways to make change, assuming that we do use the first kind of coin, sort of fixes that dime in place in the first of our like coin slots. And therefore, the number of ways to make change, assuming you use the first kind of coin, is equal to the number of ways to make change for the amount that remains after using the coin of the first kind. Because so you've put a dime in that first slot. Well, then if you want to, so that's fixed. So this is the part that changes, and then you can't figure this out with the total amount in mind. So in this example, we've got 30 cents, making change on 30 cents using dimes, nickels, and pennies. You can't do it on 30 cents for this part because you've already assigned the first coin slot to the dime. So you've got to subtract, right? You got to do A minus D, the total amount minus the denomination of that first coin. Or else, because if you didn't do that, then you'd say, well, okay, so we want to make change on 30 cents, so we'll put the dime in the first slot, and then say you don't subtract, so then you're like, okay, so then we got to make this add up to 30 cents, so then we'll do 3 dimes. And it's like, no, because you've already made part of the change, essentially. You said that the change that you're making for 30 cents is going to involve one dime and some other stuff. That's another way to, that's for this set of change making, there's going to be a dime involved, and then just the other details are what matter or would vary, and you've got to count those up. So, so there's that. And then there's the other part of this, which is the total number of ways to make change for some amount is equal to the number of ways to make change for the amount without using any of the first kind of coin. And so remember, the initial premise here was observe that the ways to make change can be divided into 2 groups: those that do not use any of the first kind of coin and those that do. Right. So then the number, so this part of it, the number of ways to make change for the amount without using any of the first kind of coin, that's just the other side of the the coin, so to speak. We need to add up 2 things to get the total number. And so for that, you just don't use any dimes. You just figure out, okay, how many ways can I make 30 cents without using any dimes? And that is more straightforward, I think. This part and like why this is true was, I thought, very tricky. But this part seemed pretty straightforward. So I did just like my own, because this is oh, I wonder if because I lost some vid somehow again, and I took a break. I don't know if I adequately explained this. So this is this is from renomad.com guy's blog. This example, I just like pasted it because I didn't like the scrolly thing, the frame scroll. And then I made my own simpler example, even easier, just to try and really get a handle on it myself. So okay, so what I did was I said, okay, let's do 20 cents using dimes, nickels, and pennies. So I have the dime constant, and then 1 dime, 2 nickels, 1 nickel, 5 pennies, 10 pennies, and that's 4 ways, and then I do it with no dimes, and then I get a total of 9 ways to make change. All right, so I think I've got a handle on this now. So what does SIPC say? Thus, we can recursively reduce the problem of changing a given amount to the problem of changing smaller amounts using fewer kinds of coins. Consider this reduction rule carefully and convince yourself that we can use it to describe an algorithm if we specify the following degenerate cases. Degenerate. That's not, this must be some technical usage having declined. Debased. Interesting. I'm just curious. Lost, debased, characterized lower standards, breaking up into a product of factors of lower degree. Okay, that sounds maybe more. There must be, yeah, there must be like a being mathematically simpler than the typical case. This has a number of, which dictionary is this? This is Webster's. Okay. Relating to a generating example that is equivalent to a simpler type. Okay. And it's just I was unfamiliar with the usage of it. Okay. So consider this reduction rule carefully and convince yourself that we can use it to apply to describe an algorithm if we specify the following degenerate cases. If A is exactly 0, we should count that as one way to make change. Well, A is the amount. You were making change on amount A. So I guess it's like we give you nothing and that's your change. Okay. If A is less than 0, we should count that as 0 ways to make change. Right, you can't give people negative change. If N is 0, we should count that as 0 ways to make change. All right, so I got some help here. I was stuck on why the this bit where it says if A is exactly 0, we should count that as one way to make change. Like why that would be the case. And I said, in the Discord, the Fallible Ideas Discord, I'm not clear on why if amount A is exactly 0, we should count that as one way to make change. A is the amount you're making change on. If the amount is 0, then you can't make change. And then Curie said, A is the amount of cents left to deal with. If it hits 0, you won. The coins you already selected did make the change. And then my follow-up to that is, so you want to count that last iteration or whatever of the algorithm running. You want to make sure that, like, as you're making the change to take the amount to 0, you want to make sure you capture that as a way of making change, I guess. So I think that's a bit clearer now. So then I think I understood the rest. If A is less than 0, we should count that as 0 ways to make change. Right, okay, so now I was just thinking of it in a different confused way earlier, but like if you're running this algorithm and you go below 0, you don't want to count that. It's like if, I don't know, if you try and it's like the amount is 5 cents that's left to make change on, and you try and use a dime to make change on it, then you don't want to count, because then you're negative 5 cents. You can't, that's not a valid, it's not a valid change making. So you don't want to count that. And then if n is 0, we should count that as 0 ways to make change. So I was still a little confused, so I found this Quora post. There we go. Particularly this part. This is basically explaining this stuff over here. So if the amount comes in as less than 0, that means the amount had a denomination that was too high. The change option is effectively rejected by not adding anything to the ultimate result, returning 0. That's if less than 0. So basically, this middle thing over here. If kind of coins reaches 0, that means whatever branch made that call ran out of kinds of change. The combination of denominations in that branch was too small. The principle at work here is that a cashier typically wants to use the largest denominations possible to give the customer the least number of coins. For example, if they needed to return 50 cents, it would be inappropriate to give the customer 50 pennies. Wait, I'm confused about that, because I thought that we were considering cases where you give like a ton of pennies. We're just trying to count up the different ways you can make change. So I know that that's right. All right. So I'm struggling a bit with with understanding the SICP stuff I'm on. And I was looking at Simply Scheme, and I think it has some relevant content. So I think I'm gonna stop the video here, and the next video, I've gone through most of Simply Scheme before. I forget exactly how far I got, but I think what I may do is, I see they talk about trees here in chapter 18. I assume this is all, yeah, recursion stuff. Recursion. Okay. And it mentions lists being useful for the structure reason. So I think my tentative plan is the next video that I make on my like super computer science focused stuff. I'm going to take SICP. I'm going to try and take it from chapter 17 and work through that and work through 18, and then loop back around to the SICP stuff and hopefully have a better idea of what I'm doing. Cause yeah, I'm like making, like I'm sort of fumbling my way through, but like I feel like it might be time to go to an easier difficulty level for a little bit. So I'm going to take a little detour. Okay. That's the end of the video.